Hello, my name is Joe Archer, and today I will talk about the advantages of a train ship. A train ship offers faster and cheaper transoceanic freight by minimizing labor, energy, time, and cost. So what is a train ship? How is it built, and why does it offer design advantages? A train ship is effectively a transoceanic train ferry. It is a way to move train freight across the ocean without having to transfer it to and from a ship, but instead provides a means of just driving a train on a ship and then driving it off of the ship at an overseas location. It is most affordably built by constructing an extrusion die consisting of adjacent conveyor belts, which are then arranged to form an A-shaped concrete profile, where the legs of the A are hollow. The extrusion process itself consists of little more than a continuous concrete pouring operation, where the concrete is pulled out of the die against tension imparted to the reinforcing cables as they pass through electromagnets. The final result is what is in effect a really long, enclosed pontoon boat with pre-stressed concrete pylons. There is a case to be made that a ship train could be made of iron and still be cost effective, and possibly more cost effective, because of its weight advantage. Fuel savings might very well pay for the added fabrication expense. Ideally, iron is the preferred fabrication material. However, a pre-stressed concrete profile offers savings up front, which factors heavily in the initial launch of a concept, and is presented here because of its lower fabrication cost. A cost-benefit analysis of this concept shows that this concept is more advantageous in proportion to the value of time. If the freight being delivered is not time sensitive, the advantages of a train ship are still superior, they are just not extraordinary. But because of the time superiority it offers, it may become the de facto shipping method in the future. Extending from the bottom of the two side flotation chambers are two thin-walled sheets running the length of the train to trap air underneath the chambers on each side of the A profile of the train ship. These sheets are akin to deep, straight dorsal fins or rudders protruding down into the water. At the front of these air-trapping fins is a flexible membrane that is pressed against the surface of the water by the trapped air pressure. At the back is a rigid flap that keeps air from escaping out the back. This front membrane prevents air leakage out the front while allowing only the air pressure between the sheets to resist the oncoming water. The depth of the fins is designed to hold the train 3 feet above the average water level of the sea. As the train moves through the water, the impact resistance to forward motion is around 5 psi of air pressure, acting against the stationary water in front of the sheet trapped air. When motionless, the flexible membrane at the front of the train is vertical. As the train picks up speed, the membrane assumes a near horizontal but sloping downward orientation. At 100 feet back from the front, the water level may only be 2 feet below the surface, even though it is being acted upon by 5 psi air. Ultimately, the water level between the sheets will approach around the 10-foot deep in response to the 5 psi of air holding it down. The advantage of this concept is that it effectively eliminates wake and its significant energy expenditure. Instead of slamming water out of the way and creating a wake, this design uses air pressure providing buoyancy to gently push the water down as the trapped air channel is passing overhead at elevated speed. Ideally, the fins would be optimized if they were made of a microporous material that lets microbubbles form on the side of the sheet that is in contact with water. This concept is used on high-speed torpedoes, where an infinitesimally small film of air reduces surface drag. With these two principles, and the fact that a long vessel is automatically faster and more efficient than a wide vessel, means that there is a case to expect 100 mile per hour or greater train speeds. This then means that the typical 3-week trans-Pacific trip might be done in 4 days. The estimated fuel savings are not easily quantified, but if we conservatively assume an equal fuel consumption, just the time difference will decrease fuel consumption by 80%. Regardless, it is almost certain that it will not burn more fuel just by virtue of being long and narrow. But perhaps the most important advantage of a ship train is that it would not need a port, nor would the train need to be loaded and unloaded. The operating concept of a ship train is to enable a train to pull up to a simple railroad pier, roll a train out of the ship, and then take in another train, and then pull out. What this concept offers the elimination of the two cargo transfers from a train to a ship and then back to a train. Instead of waiting a week to dock and days to unload and offload, it can be done in under an hour. Because there is no loading, there is no need for wharf cranes and taking turns in port. When you consider the time and expense of transferring cargo in combination with logical fuel and time savings, and then consider the cost and ease of fabricating such a train, the cost-benefit analysis is overwhelmingly positive. As great as the cost and operational advantages may be, the cost of building such a ship is an even more outstanding advantage. For a typical train, you might estimate a 20-foot diameter tube for the train and two more 20-foot diameter tubes for each flotation chamber. With 1-foot thick walls, such a design can float about 40,000 pounds per linear foot. A typical rail car is about 2,000 pounds per linear foot, and the concrete train itself is about $30,000 per linear foot. Each tube would use a little over 2 yards of concrete per linear foot, so that the train itself would use about 7 yards per foot, for a raw material cost of under $400 per foot. A 2-mile train of 100 cars then would require about $4 million in concrete and a similar amount in steel reinforcement. It might be possible to build this for $10 million. In that container ships are about 10 times that for a comparable weight, the cost per unit freight compares favorably with large container ships and might save as much as 80% their cost. However, a ship train that is 5 times faster is also 5 times more productive, such that, for a similar capital investment, 5 times as much freight is moved at a near 100% reduction in labor costs for all the 5 times as much freight. There is a case to be made that a ship train may offer as much as 80 to 90% reduction in total cost. But perhaps even more importantly, a ship train eliminates the waste of the most valuable type, time. Being able to provide a 5 times faster service could be argued to be worth 10 or even 50 times the cost, depending on the product or the emergency. So that even if a ship train actually costs more than a slow cargo ship, it would probably be an opportunity just because of the time it would save.